So with our next rational function here, we need to again, first of all, see if we can factor numerator and denominator. X squared minus 3x minus 10 can be factored into x minus 5 times x plus 2. And our denominator, x squared minus 2x minus 15, can also be factored into x minus 5 times x plus 3. So looking at this, we can cancel out x minus 5 against x minus 5, which makes it easier for us because now we only have to look at this part to graph it. But let's come back to that other part later because we do have a domain restriction down here in the denominator. So our horizontal asymptote is going to be where the two coefficients divide each other. In other words, our horizontal asymptote is y is equal to 1. Our vertical asymptote is where our denominator turns to 0. In other words, where x is equal to negative 3. Let's look at our x-intercept. The x-intercept is where the numerator turns to 0. In other words, at negative 2. X plus 2 is equal to 0 when x is equal to negative 2. In other words, negative 2 and 0. And let's also find our y-intercept. The y-intercept is the value we get when x turns to 0. So then we only have 2 over 3 left. In other words, f of 0 is 2/3. The coordinates would be 0 and 2/3. Okay, now let's go and plot everything we have. We have a horizontal asymptote at positive 1, a vertical asymptote at negative 3, and we have an x-intercept which is at negative 2 and 0, and a y-intercept which is at 0 and positive 2/3. So just underneath the horizontal asymptote. We need at least one more point to tell us what the graph is going to do to the left of our vertical asymptote. So I'm going to look for the y value if x is equal to negative 4. F of negative 4 is equal to negative 4 plus 2 over negative 4 plus 3, which is equal to negative 2 over negative 1, or just positive 2. So we got negative 4 and 2 as another point. And now we can go ahead and graph. This part goes and it approaches our vertical asymptote, and it also approaches our horizontal asymptote. The other part comes from down here, going here, approaching a horizontal asymptote more and more. As we get to positive 5 though, we have to be careful because now we need to remember what we cancel out up here. X minus 5 in the denominator. That means if x is 5, we have a denominator of 0, and this is a domain restriction. So this value doesn't exist in our graph, and we have to show this by making this an open circle, and then we can continue onwards. This open circle, which is like a hole in our graph, is called a removable discontinuity. A removable discontinuity is a hole created by a domain restriction that gets cancelled out when we simplify. This is what we did, right? And a removable discontinuity is just a point. It won't lead to an asymptote. It's just a point, and that point we have to leave blank in our graph. Let's take a look how our calculator did this. Here we got our function that I already put in, and if we look at our graph, look how this part goes to positive 5, and here we have a hole where there are no pixels. This is a hole, and we call this a removable discontinuity. Now let's go to our last case when m is greater than n. When m is greater than n, we have no horizontal asymptote, only what we call a slant or oblique asymptote. And we find this using synthetic division. Yay, synthetic division. Remember, we did this a while ago, and here it comes back and we get to use it again. Vertical asymptotes and x-intercepts, again, are exactly the same way, found the same way. The vertical asymptote is where the denominator turns to 0, and the x-intercept is where the numerator turns to 0. Let's work on our slant asymptote first. Remember how to set up our synthetic division. We use the coefficients only, 1, -4, -5. And this gets divided by the 0, not by the factor. So we take the opposite sign of this number, +2. Bring down the 1. 2 times 1 is 2. Add these two together. -4 plus 2 is -2. 2 times -2 is -4. Add these two together. We get -9. We have a remainder, but that's not a problem. What does this tell us? We've got these numbers down here, 1, -2, -9. Remember, this tells us that our function is now 1x minus 2 plus a remainder of -9 over x minus 2. Now, if our x's get really, really large, what happens to our remainder? The remainder with a really, really large denominator gets very small, and that doesn't matter to us anymore at that point. So what really matters and what tells us how our slant asymptote is going to look is the first part, x minus 2. So we have a slant asymptote at y is equal to x minus 2. We have a vertical asymptote, of course, where a denominator turns to 0, x minus 2. That means the vertical asymptote is at x is equal to 2. And we have an x-intercept where our numerator turns to 0. In order to figure this out, we need to take a numerator and factor it. And when we do that, we get x minus 5 times x plus 1. So we actually have two x-intercepts, and the x-intercepts are at x is equal to 5 and x is equal to -1. So 5, 0 and -1, 0. So let's put into our coordinate plane what we have. We have a vertical asymptote at +2. We have a slant asymptote, which is like a linear function. Y is equal to x minus 2. That means we start at a y-intercept of -2, and then we go with a slope of 1, 1 up, 1 over. In other words, here goes our slant asymptote. And let's put in our two intercepts. Our two intercepts are at +5, x-intercepts I should say, and the other x-intercept is at -1. Let's find one more point, and that's the y-intercept. The y-intercept f of 0 is where x is equal to 0, and if that's the case, this term disappears, this term disappears, this term disappears. We get -5 over -2, which is just simply 5/2 or 2.5. So the y-intercept is at +2.5, and that's enough for us to now go ahead and graph. Remember, our graph always approaches our asymptote. So this is how the left part is going to look like, and the right part is also going to approach the asymptote. Both are vertical asymptote as well as our slanted asymptote. Okay, now on to our last example. This is another case where m is greater than n, so that means we will have a slant asymptote. So let's go and find that slant asymptote. First, our coefficients are 1, 3, and 2, and we are dividing by the opposite of this number, negative 3. Bring down the 1, multiply negative 3 by 1, we get negative 3. Add these two together, we get 0. Negative 3 times 0 is still 0, and we have a remainder of 2. That means that we have a function f of x is equal to x plus no number, but plus the remainder of 2 over x plus 3. That remainder we don't need, we don't care about, because at really large x's it will become very, very small. So our slant asymptote is just x. Our slant asymptote is, in fact, y is equal to x. And as you remember, that is our diagonal, one of them at least. We start at the origin and we go up one to the right, and this is our slant asymptote. Our vertical asymptote is where the denominator turns to 0, and that would be at negative 3 for x. X is equal to negative 3. So let's put that vertical asymptote in as well. Next, we're going to look for our x-intercepts. And for x-intercepts, we need the numerator to turn to 0, but let's factor it again to see that way more easily. And that is going to be x plus 2 times x plus 1. We do have, again, two x-intercepts. The two x-intercepts are at x is equal to negative 2 and x is equal to negative 1, negative 2, 0, negative 1, 0. And let's find our y-intercept while we're at it. Y-intercept is f of 0. Turns this to 0, this to 0, this to 0, and we are left with 2/3. And that makes 0, 2/3. Our y-intercept, plotting our x-intercepts at negative 2 and 0, negative 1 and 0, very close to each other, and our y-intercept at positive 2/3, so just under 1, which gives us a good idea of this part between these two asymptotes, but not so much about the other part of our graph. So we need at least one more value, one value which is to the left of our vertical asymptote, and I'm going to pick f of negative 4. And as you can see here on the right, f of negative 4 is negative 6. So negative 4 and negative 6 is down here. Okay, that's all we need. So let's graph our function. Coming from very close to the vertical asymptote, we cross the x-axis once, come right back up, and move very close to our slant asymptote. And the other part does a similar thing without crossing x or y axis at all. Alright, so much for this, and I will see you in class.